Thank you. All right, so yeah, if you'll recall, this was probably the first section we did of this course, but parameterizing a line segment. If we've got a line segment from, and so the line segment between or from, and this utilizes vectors, so again, like I said, been a while, but so if I'm doing a line segment from, meaning from R0 to R1, meaning the line segment that's from the tip of R0 to the tip of R1. So it's that line segment there, okay? Well, it turns out that can be parameterized by this right here. It's R of t equals 1 minus t times R0 plus t times R1. And so once you evaluate that out, that'll give you your x in terms of t, because you know what you'll work it down to is eventually you'll get, we'll do one review here, but you know you'll wind up with, you know, an x of t here, comma y of t here. That can be your, so you'll see. You may not remember, but hopefully it'll all come back to you. Maybe not, but here's how it goes. So the line segment from 5,3, negative 5,3 to 0,2. We want the easy for me to not say, parameterization of that, because that's what we need when we do these line integrals. So here's one way to do this. All right, so we're going to call just R0 will be this vector to that point as well, and then R1 will be the vector to that point. And so through this little formula here, R of t, 1 minus t times the R0 plus t times the R1, just crank that out, see what that gives me. So that would be what, this 1 minus t times these would be negative 5 plus 5t, comma 3 minus 3t, plus then of course this would be 0, 2t. And so we add those together, we have negative 5 plus 5t, comma 3 minus t. Well, what we get out of that, is that right? Did I do that right? What we get out of that is, yeah, so this can be our x. And this can be our y. So it does give us a way of parameterizing this. Oh, I forgot one thing. Very important thing. The t values on this always range from 0 to 1. Forgot that. So no matter what this turns out to be, the t values are 0 to 1. So that's pretty nice. When you think about doing these in terms of a line integral, you're going to evaluate from 0 to 1, so that's going to make it nice. But you can see this works because if you do t of 0, what do you get? T of 0, you get negative 5, 3. And if you do t is 1, negative 5 plus 5, you get 0. 3 minus 1, you get 2. So it works. That's a nice little handy formula if we ever need do that. Okay, so let's see where we can use that. Evaluate line integral over C 4x cubed ds. Oh, where C is line segment. From -2, -1 to 1, 2. So again, to do this, I need to write C as parametric, in parametric form. Well, so one way to do this is just what we talked about. You'll assign these R0, R1, the vectors associated with those points. And then R of t is 1 minus t times your R0 plus t times your R1. What does that give me? Well, again, we write it out, -2 plus t, 2t, comma, -1 plus t, plus then your t, 2t. So what do we got? So you add the components. So it'll be -2 plus 3t, comma, -1 plus 3t, which means our x is going to be -2 plus 3t, the y is going to be -1 plus 3t, and again, like I said, always t is 0 to 1 for that. Okay? So it's just a process to get our line segment there parameterized. So now we can evaluate this line integral. For x cubed ds. All right, so again, the line integral, just to rehash that, we do a to b f of x of t, comma y of t, times the square root of the sum of the derivatives, dx squared derivatives, dx dt squared plus dy dt squared dt. Okay, so what this means, so just change this, well, we know we've got a to b, 0 to 1. We change, what this means is just rewrite this with your parametric formulas over there. And the only thing here involved is x again, so it's 4 times, what would be -2 plus 3t to the 4th, third. Then you do the square root of dx dt squared, so this is going to be nice because the derivative is just 3, so that'd be 9, plus the derivative of the y squared, which will also be, derivative is 3, so the derivative squared would be 9. So that, not too bad of an integral, is it? This is just a number, that's just a number. It's a little u substitution. Du is 3t, so d over 3. Yeah, so we wind up before square root of 18, change that to 1. U to the third, and then dt is d over 3. Yeah, so the integral winds up being 4 square root of Well, that actually works out pretty nicely, doesn't it? Because you change that to 3 square root of 2, you got 3 square root of 2 divided by 3. So it just winds up being 4 square root of 2. Follow all that. And it even works out nicer because, yeah, we'll get 1/4 u to the 4th here, so the 4 is going to cancel. If we change it back to t, it'd be negative 2 plus 3t to the 4th. And the good news is we're going from 0 to 1 of that. So you get the square root of 2. Negative 2 plus 3 is 1. So 1 to the 4th, 0. So you got minus that negative 2 to the 4th. So that's 16. You got negative 15 square root of 2. Is that all right? Messed up there anyway. That's what I got before, so I'll say we're okay there. All right. Let's do the line integral over C but our function's three variable. And I think they're nice about this. They're going to give C in parametric form. Well, I say that. You may have to change, you may have to do a line in parametric form. No, I don't think you have to do that here. Well, turns out in that case, do the same thing as we did with the two variable situation. We're going to change, and then they'll also give your A and B for T here. Yeah, you're going to do the very same thing. We're going to change this part over to parametric counterpart, so it's going to be, just do your evaluate f, x of t, then y of t, and z of t. May not have to use all of them if all the variables aren't there. But then the other part, just like over here, it's kind of the arc length part of it. You do the square root of the derivative squared, sum of the derivative squared. So it's no big surprise here. Okay. You just have one more variable to get the inlet possible. All right, so here's one. Line integral over C, x, y, z, ds. Where C is the helix given by x equals cosine t, y equals sine t, z equals t, 3t. And t is 0 to 4 pi. So yeah, one step is done for us. We've already got the parametrization. So that's nice. Anyway, All right, so here we go to the conversion here, make sure we're evaluating it. All right, so x is cosine t, so we have cosine t. Y is sine t, so we times sine t. And then z is 3t. All right, then, rest of it, well, you do the square roots of the derivatives. The derivative of the x is negative sine t, so you have negative sine t squared. Derivative of y is cosine, so you have cosine t squared. And the derivative of z is 3, so you have 3 squared. I'll take a look at that. This square root, oh, and it's 0 to 4 pi. Because that's the range of t there. Yeah, this square root turns out pretty nicely. Sine squared plus cosine squared is 1. So I have 1 plus 9, so we have the square root of 10 there. The other thing, again, you know, if it was just sine t, cosine t, we just do it with a little u substitution. But that 3t kind of throwing that off. So here's what we're going to do. Let's change this over using the double angle. Cosine, sine of 2t is 2 cosine t sine t. So half of sine of 2t is cosine t sine t. So this is kind of condenses down, be helpful here in this case. Cosine of 2t. With me there? So let's just bring all this, the 3, the square root of 10 and a half out. So it's 3 square root of 10 over 2. 0 to 4 pi. Cosine, let's do it, 3t times cosine 2t dt. Well, unfortunately, no, u substitution doesn't work there. The next best thing, I guess, is integration by part. Just review that. Nothing else. We haven't done that in a while. All right, so we're going to do the integral of 2 cosine t, 2t dt. U equals t, and then cosine 2t, or dv, is cosine 2t dt. Well, the derivative of that is just dt, or du equals dt there. Remember the integration of this, so we have v would be, that's just a simple substitution. It's going to be a half sine of 2t. You can go through if you want. But and so by parts, you got uv minus the integral of v du. So u times v, so it's t times that, so it'll be a half t sine 2t minus the integral of 1/2 sine 2t dt, and that's an easy enough one. Be 1/2. Again, it's just a little simple u substitution. What it amounts to is we'll have another 1/2, and again the sine is negative cosine. So we wind up with a half t sine 2t, I believe, plus a fourth. You got a minus and a minus. Cosine 2t is what that integral winds up being. Oh, what did I do? Messed up. Nobody stop. It's sine of t over 2. I put cosine of t over 2. So, this is where we're at. Change all those to sines, and then the others will be cosines. Yeah, so this will be negative cosine. Right? Yeah. Okay, so that changes everything. All right. Maybe I should just start. Okay. Try this again. So UV would be negative 1/2 t cosine 2t minus the integral of v du, so the integral of, so we minus 1/2 cosine 2t dt, which would be minus 1/2 t cosine t 2t minus my plus. Again, you'll have that half, but then u substitution, you'll have another half sine of 2t. Now we go. All right, so bring that over. All right, so it'll be minus 1/2 t cosine 2t plus 1/4 sine of 2t, and then we're going 0 to 4 pi. At least one of those is going to be good. Each case. All right, so yeah, in both cases the sign's going to be 0, 4 pi, 0. Both are going to give you 0. 4 pi, 8 pi, when you plug it in, so we'll have negative 1/2 times 4 pi times cosine of 8 pi, but that's 1. Like I said, the sine of 4 pi is 0, or 8 pi, anyway. And then the 0 gives you, oh, that's 0 too. Because you'll have 0 times 1, that's 0. The 2 will cancel, and that will cancel that. So I'm seeing 3 negatives, 3 square root of 10 pi. All right, is that good? Look okay? All right.